Right. So yeah, thank you for being here, and thank you for allowing me to talk a little bit. So I'll be rambling on a little bit about some research that I've done for my PhD. As you can see, that will be on something called critical collapse of a perfect fluid. So I don't really expect, and many people in the audience really to know what critical collapse is. So I will start a little bit by discussing what it is and show you some nice, hopefully some nice results. So in critical collapse, if you were to ask me in one sentence, what is this about? I would simply say the following. So critical collapse is the study of the phenomena that usually are called critical phenomena that happen at the threshold of black hole formation. And one of the main stars of critical phenomena, if you want, is something that's called a critical solution. And one thing that's quite interesting about this critical solution is that it has several interesting properties. So one of them is called universality. And by that, we mean that it doesn't depend on your initial data. It has a single growing mode. So if you just do perturbation theory, it has just a single growing mode. And it's self-similar. So by self-similar, you can think of the usual Newtonian equivalent, which is to say that the solution only depends on radius over time. And so just to give a little bit of an idea of what is happening, there's usually a well-known picture that usually everybody's familiar with when they do a little bit of critical collapse, and that's the following. So this picture is trying to show the entirety of phase space in GR. You have this curve that shows a one parameter family of initial data that's parameterized by a parameter called little p. So you can think of p as, for example, being the initial amplitude, let's say, of the initial data. And the arrows that go then from this line, these arrows are evolutions, time evolutions. And so you can think of, for example, if your initial data is your initial amplitude, and if your amplitude is large enough, you can think that your initial data is then going to be driven towards collapse, and you're going to get a black hole by the end of the day. On the other hand, if your parameter is sufficiently small, you're not going to get a black hole. Instead, your initial data will start contracting a little bit because of its self-gravitation, but eventually it's going to explode, and asymptotically, it will just leave a flat space behind. And so you can think that you have those two completely different end states, black hole on the one side, and basically not black hole on the other side. And then one question, naive question that you could ask is, what happens if you then fine-tune your parameter right at the threshold between these two things? And so your phase space is basically divided into these two different end states by, in this picture, by this two-dimensional sheet. And so when you start on an initial data that's right on that sheet, it's not going to collapse into a black hole, nor is it going to disperse to infinity, but instead you're going to get something else. And that's going to be, it will turn out that the spacetime that you're going to get will contain a naked singularity. And so one way you can sort of see why that's the case is that once you start, for example, with your initial data on the side that's going to create a black hole, and then you're trying to fine-tune your parameter closer and closer and closer to the threshold, you're going to get a black hole by the end of the day. But what happens is that the black hole mass is going to get smaller and smaller as you get closer and closer to the threshold. On the other hand, if you start with initial data that doesn't create a black hole, you're still going to get something that scales, but instead it's going to be the density of your matter, or the curvature of space-time, that's going to get larger and larger and larger. And so you can think of this critical point as being basically the combination of those two things: a black hole on the one side, a black hole whose radius is vanishingly small, or on the other side, curvature that becomes arbitrarily large and still visible from null infinity. And so these particular things, they scale. In fact, they scale as a power law. And so there's going to be associated critical exponent that comes with this. And so one thing that's quite nice with critical collapse is that it therefore gives you basically a way to create arbitrarily small black hole, or respectively creating spacetimes which have arbitrarily large curvature that's visible from null infinity. And for one of those reasons, it makes critical collapse actually very interesting for both the weak and the strong cosmic censorships, and as well for quantum gravity. And so this is a particular field that has now been going around for about 30 odd years. And now, many different matter fields have now been have gone under consideration, and we'll be having a look at one of them. So the case of the fluid with linear equation of state. So
Sorry, Patrick, just to interrupt you slightly, I think we're missing the bottom of your slides from the screen share.
okay, let's see.
Your screen share at the moment ends on the line which ends evolves to a naked.
Oh, I see. Let's see if I can reduce it like this, maybe.
Yeah, I can see everything now.
Okay, cool. Yes. So now to go into our setting. So axisymmetric fluid in 2+1 dimensions. So we have then the usual metric with the lapse for the dt squared component. So in typical spherical symmetry. So that's one thing that happens when you're in 2+1 dimension. It makes 2+1 dimension much easier to deal with, is that even though you're in axisymmetry, everything still depends on your time and radius coordinates. And so that makes, of course, the computation, both numerical and analytical, quite a bit easier to deal with. And so we just consider a typical perfect fluid stress energy tensor. So we have rho, that's the usual density, capital P is the pressure, UA is the full velocity, and we're going to consider a linear equation of state with linear coefficient kappa. Now, one drawback that comes with working in 2+1 dimensions, so the price you have to pay for this simplicity, is that if you want to actually talk about collapse, it turns out that in flat space, whatever your initial data is, it will never actually collapse into a black hole. And for this actually to work, you have to introduce a negative cosmological constant. So that's basically the price to pay to work in 2+1 space-time dimensions. And so we'll be working then with this parameter L that's of dimension length, and that basically parameterizes the length scale of anti-de Sitter. So now I'll just go. So I'll start with this configuration. I'll start with some initial fluid, so you can think of like a Gaussian, for example, and I will then fine tune it more and more to the threshold between those initial data that collapse and those that do not. And so here I'm going to show you the first set of results that I have obtained. So that's the results that you have where kappa is sufficiently small. So kappa being in particular smaller than about 0.42. So what happens here is that, so this plot should be read from right to left. So on the right, you have every point in this plot is basically a specific initial data. And this is the initial data that eventually collapses into a black hole. And once it collapses, we just record the maximum, the mass, as well as the spin of the black hole once it eventually collapses. And the orange one is going to be the maximum curvature for those initial data that do not collapse. And so what you can see is that once you start, for example, so every curve is a different type of initial data. And here I'm basically parameterize the different type of initial data by the initial angular momentum that we have. So for example, on the very bottom blue curve, you have an angular momentum that's relatively small. And so what you can see is that as you fine tune to the initial data, it starts to go down a little bit, but then eventually it settles down to some constant value. And in a similar way, when you look at the mass, so the mass of the black hole, or respectively the maximum curvature on the side that doesn't collapse, similarly, it just seems to flatten out into some constant value. And even if you start cranking up the initial angular momentum, you get effectively the exact same qualitative features. So even at a spin to mass ratio that's relatively high initially, the initial data is effectively going to become stationary. So that's effectively being implied here. The dotted curves are exactly the same thing, except for kappa being a little bit larger than 0.42. So that way you can sort of see that there's going to be quite a bit of a difference once kappa is a little bit larger. Now to say a little bit the same thing in a different plot. So this is a plot for a specific time evolution. So here you just read it from, as usual, from left to right. So this is a specific time evolution for an initial data that is at different fine tuning from the threshold. So sub 6 to sub 15 simply means I take initial data where the parameter from the threshold, P minus P star, is getting smaller and smaller and smaller. And so you're closer and closer to the threshold. And so I plot on the top curve 1 over the central density. On the bottom curve, I plot effectively the angular momentum, the mass, and then Rm is effectively parameterizing the width of your initial of your data. So basically where the bulk of the matter is. And so you can see that during a certain phase, all of this is roughly constant, and so in particular, your solution is approximately stationary. Of course, this particular feature only holds for a specific amount of time, because the critical solution has a growing mode, and eventually this growing mode, of course, is going to pick up, and the solution will then be driven either towards collapse or towards dispersion, as I showed you in the phase space plot before. Now this is the same picture that I show you, but this time where kappa is actually bigger than 0.43. And so you can see qualitatively, the picture looks quite similar, but the main difference is now that everything actually is going down, in fact, goes down exponentially quickly. So as you fine tune to the threshold more and more, your initial data is going to decrease more and more rapidly. So you can see, for example, the central density is decreasing exponentially. So your solution basically contracts more and more. And same thing for the spin and the mass.
Sorry, Patrick, can I get you to wrap up, please?
Yeah.
We're almost at it.
And so for the last plot that I'm going to show you here, so this is a very interesting plot. So again, you just read it from left to right. So you're starting with, on the left, you have basically different types of initial data that's then being fine-tuned more and more to the threshold. And you record the spin to mass ratio of the black hole that you get. And so what you can see from this plot is that as you fine-tune more and more to the threshold, the spin to mass ratio actually increases as you fine-tune. And in particular, it's going to get, the black hole that you're going to get is going to become arbitrarily extremal as you fine-tune more and more to the threshold. And I think that was the entire thing. Thank you. Thank you for listening.